All right, let's continue with our study of the kinematics that underlies continuum mechanics. In the recent previous segments, we've studied motion. We've studied the fact that there are at least two descriptions of motion, the Lagrangian and Eulerian descriptions. And then we also talked about the material time derivative. Today, we're going to move on and talk about perhaps the first aspect that really makes continuum mechanics special. And we're going to talk here about what we will, essentially about the distortion of solid and fluid bodies. So, while earlier we studied rigid body motion as an important example, we'll come back to that later. But for now, we're going to start studying about deformation itself. And by deformation, we mean something like distortion, right? So we have our solid body, and we are now talking about what does it take how do we describe this type of motion, right? Where the body is really distorting and perhaps moving along as well. Okay, so this is what we want to talk about, and in general, this is what we mean by deformation. So here's the outline of the next few segments. We're broadly going to talk about deformation. Okay, and in particular, we are going to talk about how deformation is applied to various geometric objects. In particular, we're going to talk about the deformation of curves, surfaces, and volumes. Okay? And you can see how this proceeds. Curves are thought of as one-dimensional objects, surfaces as two-dimensional objects, and volumes as three-dimensional objects. Okay? So, we'll do this first. The next thing we will go on to doing is talking about, we'll talk about measures of strain. Right, and this for now simply means how do we define strain. The next thing we'll do is talk about an very important idea called the polar decomposition. We will see that it's an important way in which we, so to speak, decompose the deformation into its most important aspects. And the fourth topic we will cover is the idea of the rate of deformation. Okay, so let's start with the first of these topics I've written up just above here. In particular, we'll start with curves and their deformation. Okay, so here's what we're talking about. As before, we have our basis, we have our continuum body, right? And observe that very conveniently, we do have a curve defined on it, right? We have this. So the question we are going to ask is that if we know how to parameterize this curve, right? If you're able to parameterize the curve, how do we then talk about the curve once the body deforms, right? As this body deforms, how do we describe the curve, the deformed curve? What we will see is that once we know how to do this, it will really set us on track to talk about deformation in general. Okay, so let's start with that. Let me just put down the sorts of things we need here. We have the basis, we have the body in its reference configuration, omega naught. Okay, And now, here's the other thing we have. Let us suppose that we have here a straight line, okay? And remember, a straight line is just r, right? And let us suppose that on the straight line, we have a parameter that we are going to call lambda, okay? Right? And just for the sake of argument, let's suppose that point is lambda equals 0. Okay, so this is just a straight line. Now, from the straight line parameterized by lambda, let us suppose that we've already constructed a map onto this body, right? So let's suppose that we have this map, which now has mapped that straight line onto a curve here. Okay? I need to label that curve, and I am going to call it gamma. Okay? It's a vector because, after all, that curve is just defined by a set of points belonging to this reference configuration, right? And for those sets of points, we refer to them by their position vectors, right? So gamma is just a collection of position vectors, okay, which gives us a curve on the body omega naught, right, on the reference configuration of the body omega naught. And since it was parameterized by lambda from that real line, we have lambda here, okay? Lambda is really just a scalar, right, because it comes from a one-dimensional space, okay? So here's our parameterization of a curve gamma, capital Gamma, on the reference configuration omega naught. Now, the body deforms, right? We undergo a deformation. We describe it as usual, general, in this generic fashion through phi, parameterized by capital X and T, okay? And now the body goes to a deformed state, labeled omega sub T. That curve gamma, or capital Gamma, has now become, let's suppose, more distorted, okay? And we are going to label this curve now, because it's in the deformed configuration of the body, we're going to label it little gamma, but note that it can still be parameterized by lambda, okay? Because if we don't want to worry too much about the deformation of the body, we could equivalently say that, well, from this one-dimensional space, we've constructed this map, which would be gamma, little gamma, okay? We could view it in that fashion. That's what tells us that we can continue to parameterize even little gamma by lambda, all right? However, we do know more. We know that gamma actually, little gamma actually, is obtained by deforming capital Gamma through the deformation, okay? So let's just put down a few more things that will help us remember all of this. Note that gamma is the set of points x belonging to omega naught that defines the reference configuration of the curve. Right? Likewise, little gamma is the set of points little x belonging to omega sub T that defines the deformed configuration of the curve. Okay, so these two observations allow us to write the following, right? They allow us to write gamma parameterized by lambda is really nothing but the deformation map applied to a particular set of points, capital gamma, also parameterized by lambda and time, right? Okay, and the fact that we have this at a particular time, we can remind ourselves of by putting a subscript t there. Okay, so this is the mathematical setting that we have. Now, we can ask ourselves the following question. Let me just redraw the configurations here. I have omega naught. I have my curve gamma, capital gamma, parameterized by lambda. Okay, and here under phi, I have little gamma. Okay, on omega t. Now, we may ask ourselves the following question. How do we write out the tangent to capital gamma? Okay, so if I were to ask you to describe the tangent to capital gamma mathematically, how would you go about doing it? Think about it for a second or two. The key to doing that is to observe that the tangent is generated as we vary lambda. Okay, because as we vary lambda, we march along the curve capital gamma. What this should tell us very clearly is that the tangent to gamma, to capital gamma, parameterized by lambda, is simply the derivative of gamma with respect to lambda, right? And likewise, the tangent to little gamma is, and I'm sorry for squeezing things in here a little, derivative of little gamma with respect to lambda. Okay? So now, when we asked first the question about, we asked ourselves the question, how do we describe this curve being deformed? We can reduce that question to asking ourselves, how do we define the mapping of the tangent to the reference curve here? So my index finger here indicates the tangent to the reference curve, right? Right now. We say, all right, we have this tangent to the reference curve. Let us now deform the body and thereby deform the curve as well. I'll do that. And unfortunately, I can't put my index finger back there. Okay, I'll try that. All right, there we go. The body is deformed. Here is a new tangent to the curve in its deformed current configuration. So we are asking the question, what is the relation between the reference tangent and the deformed tangent? And by doing so, we will effectively have effectively covered the question of how does the curve deform, because if we can describe the tangent, we can thereby describe the curve by just integrating. Okay? So our question of how the curve deforms is reduced to the question of how does the tangent get mapped. Okay? So the mapping of gamma, capital gamma to little gamma is defined by the mapping of their tangents. Okay? So, this is actually not at all difficult to do. Let's start with d little gamma derivative with respect to lambda. Okay? This is the tangent in the current configuration. This, remember, is just dd lambda of the deformation restricted to that set of points defining the reference curve, right? Well, we're all experts at doing this now. We just invoke the chain rule, right? So, by the chain rule, this is the derivative of phi with respect to x multiplied by or acting upon d gamma d lambda. And I've left myself room here in order to squeeze in the fact that this derivative of this derivative of phi with respect to capital X is not just a general derivative of phi with respect to capital X, but it is along the curve capital gamma. Okay, so this is for all x equal to capital gamma parameterized by lambda. Okay, that is what allows us to introduce the second factor, if you like, in this tensor vector product, the vector factor in this product, this one. Okay, the very fact that x is restricted to capital gamma of lambda. Okay, so this is essentially how tangents map, right? Because on the right hand side here we have d gamma d lambda, d capital gamma d lambda, which is the tangent to the curve in its reference configuration related to the tangent to the curve in its current configuration. This quantity here goes by the name of the deformation gradient. It's a tensor. The origins of that name should be pretty clear, right? We think of phi as the motion or the deformation in general, and its derivative with respect to the reference position is by definition the deformation gradient. Okay, so let me just put down a little more notation to do with the deformation gradient. So we will often denote, in fact most commonly we will denote f, the tensor parameterized by capital X and T, as being, this is a definition, right? Partial of phi capital X and T with respect to capital X. Okay, what that implies is that d gamma d lambda equals f d capital gamma d lambda. All right. Let me also write that out in coordinate notation. Okay, so in coordinate notation, observe that gamma can be written as gamma I EI, and we're using lowercase indices because gamma is in the deformed configuration. And a few segments ago, we decided that we would follow this notation of using lowercase indices for tensors and vectors that lived in the current configuration. Okay, and so this is because this belongs to omega sub t. That's why we're using lowercase indices here. Okay, and likewise, we would have capital gamma equals gamma sub capital I E sub capital I, and this is the reference curve, therefore we already know it belongs to omega naught, right? So what all this means for our coordinate notation is the following. It says that gamma sub I equals partial of phi sub I with respect to x sub capital I d gamma capital I with respect to lambda, and I realize I forgot to put down a d gamma I d lambda on the left hand side. Okay, there we go. Okay, this is coordinate notation. Okay, so What this says then is that if we want to talk about the deformation gradient, it's a tensor, and remember the tensor can also be written in terms of its components relative to the basis. The way we would write it is f little I, capital I, E little I, tensor E capital I. Okay, remember that the lower and uppercase indices, little I and capital I, just remind us that the corresponding, so to speak, legs of the tensor are to be thought of as living respectively in the current configuration and in the reference configuration. Okay, so F is the deformation gradient. Okay, we've already said that, I'm just repeating it. It is the deformation gradient. It maps tangent vectors in omega naught to omega t, importantly under the deformation phi. Okay. For this reason, F is also called a tangent map. Okay. Note, because we write F as F little I, capital I, E little I, tensor E, capital I, it is called a two-point tensor. Two-point because it lives both in the reference and in the current configuration, right? This, like I denoted before, belongs to omega naught, and little I belongs to omega t. Okay? And by so mapping tangent vectors, the deformation gradient tells us about how the curve gets mapped, right? Because now we know how every little tangent to this curve in the reference configuration gets mapped into the current configuration, right? And so we can then reconstruct the entire curve. Okay, we'll stop here for this segment, having thus defined the deformation gradient.